Welcome to Tech with Kaushik. This is set 22 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 22. Question number 393. Let's go. We're working with event-driven monitoring here. A company wants to implement automated observability for its AWS environment. The company needs to proactively monitor AWS health events, correlate these events with degraded application performance metrics, and trigger automated alerts. The solution must also support the creation of custom application metrics and allow the operations team to archive event data for compliance. Which solution will meet these requirements with the least operational overhead? Options. Option A. Route AWS health events to an Amazon S3 bucket using AWS CloudTrail. Query the events with Amazon Athena. Push custom application metrics to Amazon TimeStream. Create an AWS Lambda function to correlate the data and publish alerts to Amazon SNS. Option B. Use an Amazon Event Bridge rule to route AWS health events to an Amazon CloudWatch Logs log group and set the log retention period to the required compliance period. Create a metric filter that publishes a health event metric. Publish the application's custom performance metrics directly to CloudWatch. Create alarms for the health event metric and the application degradation metric. Then create a CloudWatch composite alarm that triggers an alert when the relevant health event and degraded application condition occur together. Option C. Configure the AWS Health Dashboard to send notifications directly to an Amazon SQS. Implement an AWS Lambda function to pull the queue, extract the event data, and query Amazon QuickSight to visualize the correlation between events and application latency. Option D. Enable AWS X-ray tracing for all AWS Health API calls. Instrument the application using the X-ray SDK to capture custom performance subsegments. Use the X-ray service map to correlate degraded performance with health events and configure Amazon May-See for automated alerting. The best choice is option B. Use an Amazon Event Bridge rule to route AWS health events to an Amazon CloudWatch Logs log group and set the log retention period to the required compliance period. Create a metric filter that publishes a health event metric. Publish the application's custom performance metrics directly to CloudWatch. Create alarms for the health event metric and the application degradation metric. Then create a CloudWatch composite alarm that triggers an alert when the relevant health event and degraded application condition occur together. This is the best choice because Amazon Event Bridge is the native event source for AWS health events. Routing matching events to CloudWatch logs preserves the event records for the configured retention period, and a metric filter can convert the relevant health events into a CloudWatch metric. Application metrics can be published directly to CloudWatch, and a composite alarm can correlate the health event alarm with the application degradation alarm before alerting. This satisfies event capture, custom metrics, correlation, compliance retention, and automated alerting using managed services. The other choices do not work because A. CloudTrail records AWS Health API activity, not the AWS Health event stream that Event Bridge delivers. TimeStream, Athena, and custom Lambda correlation add unnecessary components. C. The AWS Health Dashboard does not natively push events directly to SQS in this manner, and QuickSight is not a near real-time alerting engine. D. X-ray is for distributed application tracing, and May-See is for sensitive data discovery in S3. Neither is the correct mechanism for correlating AWS health events with CloudWatch performance metrics. A helpful shortcut is this. Use Event Bridge for AWS health event delivery and CloudWatch metrics, alarms, and composite alarms when event conditions must be correlated with application performance. Next up is question number 394. Here's the scenario. A company recently migrated a monolithic application to a microservices architecture deployed on Amazon Elastic Container Service, Amazon ECS. Since the migration, users have reported intermittent latency issues. A DevOps engineer needs to determine exactly which backend microservice is acting as the bottleneck during slower user requests. Which solution provides the most granular visibility into the request path to identify the problematic microservices? Here are the options. Option A. Enable Amazon CloudWatch Container Insights on the ECS cluster. Filter the Container Insights dashboards by task, CPU, and memory utilization to deduce which microservice is dropping requests. Option B. Configure the ECS tasks to emit custom metrics to Amazon CloudWatch. Create a CloudWatch composite alarm that triggers when any single microservice reports a high error rate or latency spike. Option C. Instrument the ECS microservices with OpenTelemetry, such as AWS Distro for OpenTelemetry, ADOT, and use a CloudWatch agent or OpenTelemetry collector to send distributed traces to AWS X-Ray and CloudWatch. Use the trace map and high latency traces to pinpoint the slow microservice in the request path. Option D. Install the Amazon CloudWatch agent on the ECS instances. Stream all application logs to Amazon OpenSearch service. Run a scheduled query in OpenSearch to identify microservices with log entries containing timeout errors. The answer here is option C. Instrument the ECS microservices with OpenTelemetry, such as AWS Distro for OpenTelemetry, ADOT, and use a CloudWatch agent or OpenTelemetry collector to send distributed traces to AWS X-Ray and CloudWatch. Use the trace map and high latency traces to pinpoint the slow microservice in the request path. This works because distributed tracing is the request level signal needed to identify which service contributes latency along a specific end-to-end call path. AWS now recommends OpenTelemetry-based instrumentation rather than new X-Ray SDK/daemon instrumentation. OpenTelemetry or ADOT can export traces to AWS X-Ray and CloudWatch, where the trace map and trace details expose per service latency and errors. Now let's rule out the other options. A. Container Insights provides infrastructure and container telemetry, but does not reconstruct an individual request path across microservices. B. Custom metrics and composite alarms identify aggregate conditions, not the exact service span that delayed a specific request. D. Centralized logs can help troubleshooting, but without distributed trace context, they are less direct and less granular for reconstructing a multi-service request path. Keep this point in mind for the exam. For new distributed tracing instrumentation, prefer OpenTelemetry or ADOT and analyze the resulting traces in CloudWatch/X-Ray rather than starting new instrumentation with the maintenance mode X-Ray SDKs and daemon. Question number 395. We're moving on to auto remediation. Scenario. A retail company hosts a high-traffic e-commerce platform on AWS. During flash sales, the platform experiences significant, unpredictable traffic spikes. The DevOps team needs an automated solution to detect anomalous operational behaviors across their databases, compute, and storage resources. When anomalous behavior is detected, the team must receive alerts containing context and specific actionable recommendations for resolving the operational issues. Which combination of steps will meet these requirements with the least operational effort? Choose 2. Choose every option that satisfies the requirement. Option A. Enable Amazon DevOps Guru for the AWS account. Configure the coverage to include all supported AWS resources comprising the e-commerce platform to analyze operational metrics and generate recommendations. Option B. Create an Amazon Event Bridge rule that triggers an AWS Lambda function to query AWS CloudTrail and Amazon CloudWatch metrics every 5 minutes. Program the function to calculate baseline deviations and email recommendations. Option C. Configure an Amazon SNS topic. Integrate Amazon DevOps Guru with the SNS topic to automatically send notifications to the DevOps team when operational insights or anomalies are generated. Option D. Stream all Amazon CloudWatch logs and AWS config history to an Amazon S3 bucket. Use Amazon Athena to query the logs for error spikes and visualize the results on an Amazon QuickSight dashboard. Option E. Enable Amazon Macie to continuously monitor the infrastructure. Configure Macie to publish operational anomaly findings to an Amazon SQSQ for the DevOps team to review. The correct answers are Option A. Enable Amazon DevOps Guru for the AWS account. Configure the coverage to include all supported AWS resources comprising the e-commerce platform to analyze operational metrics and generate recommendations. And Option C. Configure an Amazon SNS topic. Integrate Amazon DevOps Guru with the SNS topic to automatically send notifications to the DevOps team when operational insights or anomalies are generated. Let's look at the reasoning. Amazon DevOps Guru is an ML-powered service designed specifically to detect operational anomalies, metric deviations, and infrastructure issues. It automatically provides context and remediation recommendations without requiring manual threshold configuration. Integrating DevOps Guru with Amazon SNS provides the required automated notifications to the DevOps team with minimal operational overhead. The remaining options can be eliminated because b. Manually writing a Lambda function to calculate baseline deviations replicates the exact functionality that DevOps Guru provides out of the box, introducing massive development overhead. D. Querying logs with Athena and visualizing in QuickSight is a reactive, manual analytical process. It does not automatically generate proactive remediation recommendations. E. Amazon Macie is a data security service used to discover and protect sensitive data, like PI, in Amazon S3. It is not used for operational performance monitoring. When a question asks for automated detection of operational anomalies combined with specific remediation recommendations, Amazon DevOps Guru is the target service. Next, question number 396. A company operates a critical application on Amazon EC2 instances with multiple attached Amazon Elastic Block Store, Amazon EBS, volumes. All EBS volumes are encrypted with a customer-managed AWS KMS key in the workload account. The company's disaster recovery policy requires an RPO of 12 hours, and the environment is managed through AWS organizations. To protect backups from compromise of the workload account, a DevOps engineer must use AWS backup to copy EC2 recovery points automatically to a centralized, isolated AWS account. Backup data must remain encrypted with customer-managed KMS keys throughout the cross-account workflow. Which configuration meets these security and centralized backup requirements? Choices. Option A. Create an encrypted backup vault in the source account using a customer-managed AWS KMS key. Create a backup vault in the centralized account using an AWS-managed KMS key. Configure an AWS backup plan to create the backups and copy them to the centralized vault. Option B. Create encrypted backup vaults in both the source and centralized accounts. Use a customer-managed AWS KMS key residing in the source account to encrypt the vaults in both accounts. Configure AWS backup to copy the EC2 AMIs to the centralized vault. Option C. Create a backup plan that runs at least every 12 hours and copies the EC2 recovery points to a backup vault in the centralized account. Allow the centralized account to use the customer-managed KMS key that encrypts the source EBS volumes for the cross-account copy. Encrypt the destination backup vault with a distinct customer-managed KMS key in the centralized account, and grant the required cross-account vault and KMS permissions for the copy job. Option D. Create backup vaults in both accounts using default AWS-managed KMS keys for encryption. Configure AWS backup to take volume-level snapshots and copy them to the centralized vault using a resource-based policy. Go with option C. Create a backup plan that runs at least every 12 hours and copies the EC2 recovery points to a backup vault in the centralized account. Allow the centralized account to use the customer-managed KMS key that encrypts the source EBS volumes for the cross-account copy. Encrypt the destination backup vault with a distinct customer-managed KMS key in the centralized account, and grant the required cross-account vault and KMS permissions for the copy job. Amazon EC2 backups contain EBS snapshots whose source encryption follows the underlying EBS volumes. For a cross-account copy of a resource encrypted with a customer-managed KMS key, the destination account must be permitted to use the source key for the copy workflow. AWS backup then re-encrypts the copy with the encryption key associated with the destination vault. Using a distinct customer-managed key in the isolated account and a schedule no less frequent than every 12 hours satisfies the encryption, isolation, and RPO requirements. Here's why the alternatives are not suitable. A. A destination AWS managed key does not satisfy the stated requirement that the copied backup remain protected by company managed keys, and AWS managed keys cannot be modified for the cross-account permissions required by non-fully managed backup types. B. A backup vault normally uses a KMS key available to that vault/account. Simply attempting to use only the source account key for both vaults does not establish the required destination encryption and copy permissions. D. Default AWS managed keys do not satisfy the customer managed key requirement and cannot provide the required modifiable cross-account key policy. Here's a useful exam tip. For cross-account EC2/EBS backup copies, distinguish source resource encryption from destination vault encryption. Share the source CMK as required for the copy and re-encrypt the destination copy with a CMK controlled by the backup account. Question number 397. The focus now shifts to troubleshooting. Here's what is happening. A DevOps engineer provisions a new Amazon Elastic Kubernetes service, Amazon EKS, cluster and configures managed node groups. However, the nodes fail to join the cluster, and the EKS console displays a node creation failure. Instances failed to join the Kubernetes cluster error. The engineer verifies that the underlying EC2 instances are in a running state, and the EKS control plane is active. What is the most operationally efficient way to diagnose the root cause of this node registration failure? Review the options. Choice A. Run the AWS Support Troubleshoot KES Worker Node AWS Systems Manager Automation Runbook targeting the failing instances. Choice B. Create an AWS Identity and Access Management IAM, OpenID Connect, OIDC, provider for the EKS cluster and restart the kubelet service on the nodes. Choice C. Execute the kubectl update kubeconfig command using the IAM user credentials that initially provisioned the cluster. Choice D. Terminate the managed node group and deploy a self-managed node group using a custom Amazon machine image, AMI, to inspect the boot logs. The right response is option A. Run the AWS Support Troubleshoot KES Worker Node AWS Systems Manager Automation Runbook targeting the failing instances. The main reason is AWS Systems Manager provides managed automation runbooks specifically designed to diagnose common operational issues. The AWS Support Troubleshoot KES Worker Node Runbook automatically checks common failure points for EKS node registration, such as VPC routing, IAM instance profile permissions, security group configurations, and kubelet status, providing a detailed report with the least operational overhead. Let's quickly check the incorrect choices. B. Creating an OIDC provider is required for IAM roles for service accounts, IRSA, but it has no bearing on worker nodes joining the cluster at the EC2/kubelet level. C. Updating the local kubeconfig file configures client access to the cluster control plane. It does not fix worker nodes failing to register. D. Replacing the managed node group with a self-managed node group to manually inspect boot logs requires significant manual effort and defeats the purpose of using managed operational tools. The main takeaway is when troubleshooting standard AWS operational issues, like EKS nodes failing to join or EC2 instances failing status checks, look for AWS Systems Manager Automation runbooks. For example, AWS Support ***. They always represent the path of least operational overhead. Question number 398. Scenario. A company needs to implement a centralized artifact repository to standardize software packages across its on-premises data center and its AWS environment. The solution must provide high availability, cache packages from public upstream repositories, such as NPM and PyPI, and encrypt all artifacts at rest and in transit. Currently, there is no private network routing between the on-premises data center and the AWS VPCs. The solution must be fully implemented and operational within a week. Which solution will meet these requirements most efficiently? Option A. Deploy a cluster of Amazon EC2 instances running open-source artifact management software. Provision redundant AWS Direct Connect connections to connect the data center to AWS. Store the artifacts on Amazon Elastic Block Store, Amazon EBS, volumes. Option B. Establish an AWS site-to-site VPN connection between the on-premises data center and AWS. Create an AWS code artifact domain and repository. Configure the repository with upstream connections to the required public package managers. Option C. Use AWS code commit to store the deployment artifacts. Set up an Amazon API Gateway REST API backed by AWS Lambda to serve the packages over the public internet using HTTPS to ensure transit encryption. Option D. Provision an Amazon S3 bucket for artifact storage. Deploy an AWS storage gateway, file gateway on-premises. Configure a scheduled AWS data sync task to synchronize public downstream packages into the S3 bucket. In this case, choose option B. Establish an AWS site-to-site VPN connection between the on-premises data center and AWS. Create an AWS code artifact domain and repository. Configure the repository with upstream connections to the required public package managers. Here's why. AWS Code Artifact is a fully managed, highly available artifact repository service that natively supports upstream caching from public repositories like NPM, PyPI, Maven. It automatically encrypts artifacts at rest via KMS and in transit via HTTPS. Establishing an AWS site-to-site VPN satisfies the private routing requirement and can be provisioned in minutes, easily meeting the 2-week deadline. Deploying third-party software on EC2 introduces significant operational overhead for patching and scaling. Furthermore, provisioning AWS Direct Connect typically takes weeks or months to coordinate with telecom providers, failing the timeline requirement. AWS Code Commit is a Git-based source control service, not a binary package management repository. It does not support upstream package proxying. AWS Storage Gateway and Data Sync are used for file/object transfer, not for serving as an intelligent package manager that understands package dependencies and upstream proxying. Exam tip. AWS Code Artifact is the designated service for standardizing, proxying, and caching software packages. When a tight deadline is imposed for hybrid connectivity, a site-to-site VPN is always faster to deploy than AWS Direct Connect. Next, question number 399. This question takes us into organizations and SCPs. A company manages its environments using AWS organizations. The production AWS accounts are located in a production organizational unit, OU. A DevOps team uses an AWS code pipeline residing in a central CI/CD account to deploy application updates into the production OU. The DevOps team members belong to an AWS IAM Identity Center group that grants them administrator access to the production accounts. Recently, a developer manually modified a resource in production, causing a pipeline deployment to fail and creating an outage. A DevOps engineer must enforce that only the CI/CD pipeline role can modify resources in the production OU. However, a designated senior engineer still needs the ability to manually remediate resources in production during an emergency. Which solution meets these requirements with the most operational efficiency? Choices. Option A. Update the DevOps team's IAM Identity Center group to grant read-only access to the production accounts. Create a new permission set with administrator access and assign it to the senior engineer. Apply a service control policy, SCP, to the production OU that denies all actions except those performed by the pipeline role and the senior engineer's execution role. Option B. Remove the DevOps team's access to the production OU entirely. Create an AWS Lambda function that temporarily grants administrator access to the senior engineer when invoked. Use an AWS step functions workflow to revert the permissions after 1 hour. Option C. Apply a service control policy, SCP, to the production OU that denies all write actions. Tag all resources provisioned by the pipeline with a specific tag. Add a second SCP that denies modifications to the tagged resources by any entity other than the senior engineer. Option D. Update the DevOps team's IAM Identity Center group to allow STS. Assume role targeting the pipeline role. Apply a service control policy, SCP, to the production OU denying all modifications by any entity other than the senior engineer. The right response is option A. Update the DevOps team's IAM Identity Center group to grant read-only access to the production accounts. Create a new permission set with administrator access and assign it to the senior engineer. Apply a service control policy, SCP, to the production OU that denies all actions except those performed by the pipeline role and the senior engineer's execution role. This is the best choice because this approach successfully implements least privilege using layered defense. Removing standing administrator access from the general team prevents accidental manual changes. The SCP acts as an organizational guardrail, explicitly denying write actions unless the caller matches the CI/CD pipeline's ARN or the specific senior engineer's ARN. This guarantees that only the pipeline can deploy while retaining emergency break glass access for the senior engineer. The other choices do not work because B. Using Lambda and step functions to dynamically grant permissions is overly complex and fragile for emergency access, failing the operational efficiency requirement. C. A standard SCP denying all write actions would block the pipeline from deploying. SCPs do not inherently bypass specific roles unless explicit string not-like conditions are added to the statement. D. If the DevOps team can simply assume the pipeline role, they can use that role to manually modify resources in production, violating the requirement that only the pipeline, the automated process, performs deployments. A helpful shortcut is this. To restrict deployments strictly to a CI/CD pipeline, apply an SCP with a deny effect and a string not-like condition on AWS. Principal errand, specifying only the pipeline's IAM role and any required emergency break glass roles. Now for question number 400. A DevOps engineer is managing a critical application deployed on Amazon EC2 instances using AWS Code Deploy. A recent automated deployment failed during the application start lifecycle event on a subset of the instances. The engineer needs to determine exactly which script executed during that event and why it returned a non-zero exit code. What is the most direct way to retrieve the execution output of the failed deployment script? The choices are: Choice A. Review the application's business logic logs stored in Amazon CloudWatch logs and trace the deployment API calls using AWS X-Ray. Choice B. Connect to the affected EC2 instances and analyze the code deploy agent deployment logs located in the /opt/code-deploy-agent/deployment route/directory. Choice C. Query AWS CloudTrail using Amazon Athena to extract the detailed error messages generated by the update environment API call. Choice D. Use the AWS Systems Manager run command history to inspect the stout and stare streams of the deployment commands executed on the instances. The best choice is option B. Connect to the affected EC2 instances and analyze the code deploy agent deployment logs located in the /opt/code-deploy-agent/deployment route/directory. This works because when an AWS code deploy lifecycle event script, like before install or application start, fails on an EC2 instance, the code deploy agent running on that instance logs the exact execution output, including stout and stare. These logs are stored locally on the instance in the /opt/code-deploy-agent/deployment route/deployment logs/directory. Now let's rule out the other options. A. Application business logic logs, stored in CloudWatch, will not show the infrastructure deployment script failures if the application failed to start in the first place. C. AWS CloudTrail records the control plane API call. Update environment is Elastic Beanstalk, not code deploy. It does not capture the standard output of shell scripts running locally on an EC2 instance. D. Code deploy uses its own agent, not the AWS Systems Manager run command, to execute deployment scripts. Keep this point in mind for the exam. For AWS code deploy on EC2/on-premises, the local agent log file code-deploy-agent.log and the script execution outputs located in /opt/code-deploy-agent/deployment route/ are the definitive sources for troubleshooting failed deployment lifecycle hooks. Here comes question number 401. Next, let's move into artifact management. Consider this situation. A company stores its Docker container images in an Amazon Elastic Container Registry, Amazon ECR, repository in the US East 1 region. The company is implementing a disaster recovery strategy and must ensure that all images in the repository are replicated to a newly created ECR repository in the US West 2 region. A DevOps engineer has configured a cross-region replication rule on the primary ECR registry in US East 1 targeting the registry in US West 2. Which step is required to ensure that the pre-existing container images are copied to the secondary region with the least operational overhead? Option A. Modify the resource-based policy on the primary ECR repository to explicitly allow the ECR batch get image action from the secondary region's registry service principal. Option B. Create an AWS Lambda function triggered by an Amazon Event Bridge schedule to periodically invoke the replicate image API for all images older than the replication rule creation date. Option C. Configure an Amazon S3 cross-region replication rule on the underlying S3 bucket that AWS manages for the EC/R repository to synchronize the data to us. West 2. Option D. Manually pull the existing container images from the primary repository in us. East 1 and push them back to the primary repository to trigger the new replication rule. The answer here is option D. Manually pull the existing container images from the primary repository in us. East 1 and push them back to the primary repository to trigger the new replication rule. Let's look at the reasoning. Amazon EC/R cross-region replication relies on registry-level rules that are evaluated only when an image is successfully pushed to the repository. Existing images that were pushed before the replication rule was created are not retroactively evaluated or copied. To replicate pre-existing images, you must manually pull them and push them back to the source repository, which triggers the rule. The remaining options can be eliminated because A. EC/R cross-region replication within the same AWS account does not require explicit resource-based policy modifications on the source registry to allow the destination registry. The rule itself handles the authorization. B. There is no native replicate image API in EC/R that can be invoked via Lambda to retroactively push images. C. You cannot access or configure replication on the underlying AWS-managed S3 buckets that EC/R uses for storage. EC/R replication rules apply only to new image pushes. To replicate existing EC/R images to a new destination, you must physically pull and re-push the images to the source repository. Here comes question number 402. A company uses an AWS code pipeline to build container images and publish them to Amazon Elastic Container Registry, Amazon EC/R. The pipeline source is a GitHub repository connected via AWS Code Connections. The DevOps team requires the pipeline to trigger automatically only when developers push a new Git tag. Additionally, to prevent race conditions during rapid tagging, the pipeline must process executions in the exact order the tags are pushed, waiting for any currently running execution to complete before starting the next. Which pipeline configuration will meet these requirements? Review the options. Option A. Configure a code pipeline v2 pipeline. Define a trigger filter that includes all Git tags. Set the pipeline execution mode to queued. Option B. Configure a code pipeline v1 pipeline. Add a GitHub webhook configured to trigger on tag creation. Set the pipeline execution mode to superseded. Option C. Configure a code pipeline v2 pipeline. Define a trigger filter that includes all branches. Set the pipeline execution mode to parallel. Option D. Configure an Amazon Event Bridge rule that matches Code Connections tag events to invoke a code pipeline v1 pipeline. Set the pipeline execution mode to queued. Go with option A. Configure a code pipeline v2 pipeline. Define a trigger filter that includes all Git tags. Set the pipeline execution mode to queued. AWS Code Pipeline v2 natively supports triggering pipelines based on Git tags via AWS Code Connections. Additionally, v2 introduces pipeline execution modes. The queued execution mode ensures that if multiple executions are triggered rapidly, for example, rapid Git tagging, they wait in a queue and are processed exactly in the order they were triggered, preventing race conditions and concurrent deployment issues. Here's why the alternatives are not suitable. B. Code Pipeline v1 does not natively support Git tag triggers or explicit execution modes like queued. C. Parallel mode runs executions concurrently. This violates the requirement to wait for the previous run to finish. D. While Event Bridge could be used to orchestrate triggers for v1, v2 supports Git tags natively, providing the least operational overhead. v1 also lacks native queued mode execution natively defined in the pipeline configuration. Here's a useful exam tip. AWS Code Pipeline v2 introduces direct Git tag triggers and pipeline execution modes, queued, superseded, parallel. Use queued mode when strictly ordered, non-overlapping pipeline executions are required. Question number 403. Let's go. The focus now shifts to logging architecture. Scenario. A company applications stream high volumes of log data to Amazon CloudWatch logs. The operations team requires that the logs be searchable natively within CloudWatch for exactly 30 days. After 30 days, the logs must be retained for compliance, but stored as cost-effectively as possible. For the first 90 days after generation, the compliance logs must be retrievable with millisecond latency. From day 91 to day 180, retrieval is extremely rare, and retrieval times of up to 12 hours are acceptable. After 180 days, the logs can be deleted. Which solution will meet these requirements most cost-effectively? Options. Option A. Set the CloudWatch log group retention to 30 days. Create a CloudWatch metric stream that writes log events to an Amazon S3 bucket via Amazon Kinesis data streams. Apply an S3 lifecycle policy to transition objects to S3 standard IA immediately. Transition to S3 Glacier flexible retrieval after 90 days, and expire objects after 180 days. Option B. Set the CloudWatch log group retention to 30 days. Create a CloudWatch log subscription filter that streams data to an Amazon Data Firehose delivery stream, targeting an Amazon S3 bucket. Apply an S3 lifecycle policy to transition objects to S3 standard IA after 30 days, transition to S3 Glacier Deep Archive after 90 days, and expire objects after 180 days. Option C. Set the CloudWatch log group retention to 180 days. Apply the CloudWatch infrequent access IA log class to the log group. Create an event bridge rule that automatically exports logs older than 90 days to Amazon S3 Glacier instant retrieval. Option D. Set the CloudWatch log group retention to 30 days. Export the logs daily to an Amazon S3 bucket using an AWS Lambda function. Apply an S3 lifecycle policy to transition objects to S3 OneZone IA after 90 days and transition to S3 Glacier Deep Archive after 180 days. In this case, choose option B. Set the CloudWatch log group retention to 30 days. Create a CloudWatch log subscription filter that streams data to an Amazon Data Firehose delivery stream, targeting an Amazon S3 bucket. Apply an S3 lifecycle policy to transition objects to S3 standard IA after 30 days, transition to S3 Glacier Deep Archive after 90 days, and expire objects after 180 days. The main reason is this solution is highly cost-effective and meets all data retrieval constraints. Setting CloudWatch retention to 30 days satisfies the native search requirement while minimizing expensive CloudWatch storage. A subscription filter seamlessly pushes logs to S3 via Firehose in real time. Standard IA provides millisecond retrieval for the 90-day window, and Glacier Deep Archive minimizes costs for the rare 12-hour retrieval window up to 180 days. Let's quickly check the incorrect choices. A. CloudWatch metric streams are used strictly for sending CloudWatch metrics, not logs, to destinations. C. The CloudWatch infrequent access IA log class is cheaper than standard, but retaining logs in CloudWatch for 180 days is significantly more expensive than tiering them to S3 Glacier Deep Archive. Furthermore, IA log class does not support automated event bridge exports to Glacier. D. Using Lambda to execute daily batch exports is operationally complex and error-prone compared to a fully managed Firehose subscription filter. The main takeaway is for long-term log retention. Always use a CloudWatch log subscription filter targeting Amazon Data Firehose to stream the logs directly to Amazon S3. Apply S3 lifecycle rules to tier the data to Glacier to achieve the lowest cost. Now for question number 404. Here's the scenario. A healthcare organization manages a fleet of hundreds of Amazon EC2 instances. Strict compliance regulations mandate that all EC2 instances must be scanned weekly for missing critical security patches, and any missing patches must be installed automatically without manual intervention. The organization must also maintain an ongoing dashboard of patch compliance status. Which solution meets these requirements with the least operational overhead? Here are the options. Choice A. Deploy an AWS CloudFormation template that launches a custom AWS Lambda function to SSH into each instance weekly, execute yum update or apt-get upgrade, and log the output to Amazon CloudWatch. Choice B. Use AWS Systems Manager Patch Manager to define a patch baseline. Configure a maintenance window to run the AWS Run Patch Baseline SSM document with the install operation weekly. Use Systems Manager Explorer for compliance reporting. Choice C. Create an Amazon Event Bridge rule that triggers weekly to terminate all instances in the fleet and replace them by launching new instances from the latest AWS-managed AMIs in an auto-scaling group. Choice D. Install the Amazon Inspector agent on all instances. Configure Inspector to automatically apply patches when CVs are detected and generate compliance reports using AWS Security Hub. The best choice is option B. Use AWS Systems Manager Patch Manager to define a patch baseline. Configure a maintenance window to run the AWS Run Patch Baseline (SSM) document with the install operation weekly. Use Systems Manager Explorer for compliance reporting. Here's why. AWS Systems Manager Patch Manager is the purpose-built AWS service for automating the process of patching managed nodes. By defining a patch baseline, configuring a maintenance window, and executing the AWS Run Patch Baseline document, patches are installed automatically. Systems Manager Explorer and Patch Manager natively aggregate and visualize the patch compliance status across the fleet. Managing SSH keys and writing custom Lambda functions to execute OS-level patch commands manually is highly error-prone, insecure, and introduces massive operational overhead. Replacing instances weekly ensures fresh AMIs, but if an AMI is not updated, the instances remain unpatched. This pattern, immutable infrastructure, is valid for stateless web apps, but auto-scaling alone does not provide a patch compliance reporting dashboard. Amazon Inspector is a vulnerability management service. It detects missing patches, CVs, but does not have native functionality to automatically apply the patches to the operating system. Exam tip. When a requirement specifies automated OS-level patching and compliance reporting across an EC2 fleet, AWS Systems Manager Patch Manager is the correct native tool. Next up is question number 405. Treat this as a medium question. Here's what is happening. A software development team uses AWS code pipeline with two separate pipelines connected to a Git repository. The feature pipeline runs automated unit tests whenever a developer pushes a commit to any feature branch. The release pipeline builds and deploys the application to production whenever a pull request is merged into the main branch. Developers complain that they frequently have to wait for earlier commits on their feature branches to finish testing before their latest commits are tested. Additionally, the production deployment occasionally fails because a newer merge to main overrides an in-progress deployment from an older merge. How should a DevOps engineer configure the pipeline execution modes to resolve these issues? The choices are: Choice A, set the feature pipeline execution mode to superseded. Set the release pipeline execution mode to queued. Choice B, set the feature pipeline execution mode to queued. Set the release pipeline execution mode to parallel. Choice C, set the feature pipeline execution mode to parallel. Set the release pipeline execution mode to superseded. Choice D, set the feature pipeline execution mode to parallel. Set the release pipeline execution mode to queued. The right response is option D. Set the feature pipeline execution mode to parallel. Set the release pipeline execution mode to queued. This is the best choice because AWS Code Pipeline v2 allows configuring pipeline execution modes. Setting the feature pipeline to parallel ensures that when multiple developers push commits, each commit is tested immediately in its own isolated execution without waiting for prior executions to finish. Setting the release pipeline to queued ensures that production deployments happen in a strict, sequential order. If a new merge occurs, it waits safely in the queue until the current deployment finishes, preventing overrides and failed deployments. The other choices do not work because A, setting the feature pipeline to superseded means older commits would be canceled if a newer commit is pushed, meaning developers wouldn't get test results for their specific commits. Queued on release is correct. B, setting the feature pipeline to queued would force developers to wait sequentially for all previous tests to finish, slowing down feedback. Parallel on release could cause concurrent deployments to override each other. C, superseded on the release pipeline would cancel the current deployment in progress if a new merge occurs, potentially leaving production in an inconsistent state. A helpful shortcut is this. Use parallel mode for fast, independent feedback, like unit tests on feature branches. Use queued mode when strict ordering and non-overlapping executions are required, like deploying to a production environment. Question number 406. Scenario. A company runs a massive microservices architecture on Amazon Elastic Kubernetes Service, Amazon EKS. The security team requires comprehensive audit logs of all API requests made to the Kubernetes API server. Simultaneously, the operations team requires performance logs and metrics from the containers running on the EKS worker nodes. Both teams want to query their respective logs using a managed AWS interface. Which solution will meet these logging requirements with the least operational overhead? Choices. Option A. Enable AWS CloudTrail data events for the EKS cluster to capture API server logs. Deploy FluentBit on the worker nodes as a daemon set to send container logs to Amazon OpenSearch service. Option B. Enable EKS control plane logging to send API server logs to Amazon CloudWatch logs. Enable CloudWatch container insights on the cluster to capture node and container logs. Use CloudWatch logs insights to query both log sets. Option C. Configure the Kubernetes API server to write logs to an Amazon Elastic file system, Amazon EFS, volume attached to the control plane. Use AWS distro for OpenTelemetry to collect node metrics. Query the EFS volume using Amazon Athena. Option D. Deploy an AWS Lambda function that pulls the EKS control plane for API events and writes them to Amazon S3. Install the Amazon CloudWatch agent on the worker nodes to collect container logs. Query the S3 bucket using Amazon Athena. In this case, choose option B. Enable EKS control plane logging to send API server logs to Amazon CloudWatch logs. Enable CloudWatch container insights on the cluster to capture node and container logs. Use CloudWatch logs insights to query both log sets. This works because this is the fully managed AWS native approach to EKS logging. EKS control plane logging natively streams Kubernetes API server logs directly to CloudWatch logs with a single configuration change. CloudWatch Container Insights deploys a managed FluentBit daemon set to capture container and node logs, streaming them to CloudWatch. Both datasets can then be queried efficiently using CloudWatch logs insights, satisfying all requirements with minimal overhead. Now let's rule out the other options. A. AWS CloudTrail does not natively capture internal Kubernetes API server events, for example, kubectl interactions. Those are captured by EKS control plane logging. C. Writing Kubernetes API logs to an EFS volume is not supported natively by EKS and would require highly complex, unsupported custom configurations on the AWS managed control plane. D. Polling the EKS control plane with Lambda is inefficient and unnecessary when EKS integrates directly with CloudWatch. Keep this point in mind for the exam. For Amazon EKS observability, EKS control plane logging captures the Kubernetes API activity, while CloudWatch Container Insights captures the performance metrics and stout logs of the worker nodes and pods. Question number 407. Let's go. Take extra care here because this is a hard question. A company uses AWS organizations to manage multiple AWS accounts. A dedicated security account acts as the delegated administrator for security services. The security team requires organization-wide AWS management events to be recorded and retained in an Amazon S3 bucket located in the security account. The team must also receive near real-time email notifications through an Amazon SNS topic in the security account whenever an AWS Management Console sign-in fails in any member account. Which solution meets these requirements with the least operational effort? Option A. Create an organization trail in AWS CloudTrail that delivers organization-wide management events to an S3 bucket in the security account. Use an organization-wide deployment mechanism such as AWS CloudFormation stack sets to create event bridge rules in the member accounts and required regions that match failed console login events and forward them to an event bus in the security account. In the security account, create an event bridge rule that sends the forwarded events to the SNS topic. Option B. Create an organization trail that delivers logs to an S3 bucket in the security account. Configure Amazon may-see in the security account to scan the S3 bucket for failed logins and publish findings to the SNS topic. Option C. Create an organization trail that delivers logs to an S3 bucket in the security account. Create an AWS Lambda function triggered by S3. Object created events to parse the compressed log files for failed logins and notify the SNS topic. Option D. Enable AWS config organization rules to track failed IAM logins. Stream the configuration changes to an Amazon Kinesis data stream in the security account and use Amazon Kinesis Data Analytics to trigger the SNS topic. The answer here is option A. Create an organization trail in AWS Cloud Trail that delivers organization-wide management events to an S3 bucket in the security account. Use an organization-wide deployment mechanism, such as AWS CloudFormation stack sets, to create event bridge rules in the member accounts and required regions that match failed console login events and forward them to an event bus in the security account. In the security account, create an event bridge rule that sends the forwarded events to the SNS topic. Let's look at the reasoning. An organization trail provides centralized, durable cloud trail records in the security account. Console sign-in attempts are represented by CloudTrail console login events, but AWS service events are delivered to Event Bridge in the account and region where the event occurs. Centralizing CloudTrail log files in S3 does not automatically place those real-time events on the security account event bus. Forwarding matching member account Event Bridge events to a central event bus, and then targeting the central SNS topic provides the required near real-time notification path, while the organization trail provides retention. The remaining options can be eliminated because B. Macy discovers and classifies sensitive data in S3. It is not a console login event detector. C. Parsing delivered CloudTrail objects with Lambda is a batch-oriented custom solution and introduces more latency and operational overhead than Event Bridge event routing. D. AWS config evaluates resource configuration and compliance state. It does not track interactive sign-in failures as configuration changes. An organization trail centralizes CloudTrail storage, but near real-time Event Bridge events still originate on the source account event bus. Explicitly forward cross-account events when central alerting is required. Next, question number 408. Scenario. A company operates an application built on a dozen interconnected microservices running on Amazon Elastic Kubernetes Service, Amazon EKS. Users are reporting that a specific user workflow, generating a monthly PDF report, frequently times out. A DevOps engineer checks Amazon CloudWatch metrics and finds that CPU, memory, and network utilization across all EKS nodes are well below 30%. The application logs show that the request initiates, but it is entirely unclear which specific microservice in the dependency chain is causing the delay. What is the most effective way for the engineer to increase observability and pinpoint the exact source of the latency? Options. Option A. Enable VPC flow logs for the EKS cluster VPC. Stream the flow logs to Amazon Athena and execute SQL queries to identify which pod IP address is transmitting the most data. Option B. Instrument the microservices with OpenTelemetry, such as AWS distro for OpenTelemetry, ADOT, and deploy an OpenTelemetry collector or compatible CloudWatch agent in the EKS cluster to export distributed traces to AWS X-Ray and CloudWatch. Analyze the trace map and high latency spans to identify the microservice causing the timeout. Option C. Deploy the Amazon CloudWatch agent as a daemon set to the EKS cluster. Configure it to collect custom application metrics and use CloudWatch anomaly detection to highlight the failing service. Option D. Increase the log level of all microservices from info to debug. Stream the logs to Amazon OpenSearch service and create a dashboard tracking the total volume of debug messages per service. Go with option B. Instrument the microservices with OpenTelemetry, such as AWS distro for OpenTelemetry, ADOT, and deploy an OpenTelemetry collector or compatible CloudWatch agent in the EKS cluster to export distributed traces to AWS X-Ray and CloudWatch. Analyze the trace map and high latency spans to identify the microservice causing the timeout. The problem requires request-level dependency and latency visibility, not additional host metrics. OpenTelemetry or ADOT propagates trace context across the microservices and exports spans that can be analyzed in AWS X-Ray and CloudWatch. The trace map and span timings show exactly which downstream service consumes the time in the PDF generation workflow. AWS recommends OpenTelemetry-based instrumentation for new tracing implementations because the X-Ray SDKs and daemon are in maintenance mode. Here's why the alternatives are not suitable. A. VPC flow logs describe network flows, not application span timing or logical dependency latency. C. Custom metrics and anomaly detection can identify aggregate changes, but cannot reconstruct the end-to-end path of one workflow across a dozen services. D. Debug logs dramatically increase volume and still require manual correlation. Message volume does not identify which service span caused the timeout. Here's a useful exam tip. When infrastructure utilization is normal but a multi-service request is slow, use distributed tracing with OpenTelemetry/ADOT and analyze per span latency in CloudWatch/X-Ray. Question number 409. Let's go. A company maintains a popular open-source software project hosted in a public GitHub repository. The company currently uses an AWS code pipeline to compile the source code, but a developer must log into the AWS Management Console and manually click Release Change every night to trigger the build. The company wants to fully automate this process so that a nightly build runs automatically. Additionally, the resulting build artifacts must be made publicly available for download from an Amazon S3 bucket. Which solution will meet these automation requirements with the least operational overhead? Option A. Configure an AWS Lambda function that pulls the GitHub API daily for changes. If changes are detected, program the Lambda function to trigger the pipeline and execute an AWS CLI command to copy the artifacts to the S3 bucket. Option B. Add an Amazon S3 deploy action stage to the end of the existing pipeline and configure the action to publish the artifacts to the public S3 bucket. Create an Amazon Event Bridge scheduled rule configured to start the pipeline execution once a day. Option C. Replace code pipeline with an AWS code build project. Configure a GitHub webhook on the repository to trigger the build on every push event. Add a post-build command in the build spec.yml file to synchronize the artifacts to the S3 bucket. Option D. Add a manual approval action to the pipeline before a new Amazon S3 deploy action. Configure AWS CloudTrail to monitor the GitHub repository and trigger the pipeline daily using AWS Systems Manager automation. The answer here is option B. Add an Amazon S3 deploy action stage to the end of the existing pipeline and configure the action to publish the artifacts to the public S3 bucket. Create an Amazon Event Bridge scheduled rule configured to start the pipeline execution once a day. The main reason is this solution leverages the existing AWS code pipeline configuration, ensuring minimal operational overhead. By simply adding a native S3 deploy action to the pipeline, the artifacts are automatically copied to the target bucket. An Amazon Event Bridge scheduled rule, using a cron expression, seamlessly invokes the code pipeline API, start pipeline execution, every night, removing the need for manual invocation. Let's quickly check the incorrect choices. A. Polling an API using Lambda requires writing, maintaining, and debugging custom code, introducing significantly higher operational overhead than using native Event Bridge scheduling. C. Ripping out code pipeline and replacing it with code build just to run on a schedule is unnecessary. Furthermore, a GitHub webhook triggers on every push, violating the requirement to run a nightly build. D. Adding a manual approval action explicitly prevents automation, directly violating the requirement to fully automate the nightly process. The main takeaway is to run an AWS code pipeline on a recurring schedule, for example, nightly builds, weekend security scans. Use an Amazon Event Bridge scheduled rule targeting the pipeline's execution API. Question number 410. A DevOps team is adopting the AWS Cloud Development Kit, AWS CDK, to manage the infrastructure for a suite of independent microservices. The team wants to define reusable architectural patterns, such as a standardized Amazon API gateway integrated with an AWS Lambda function and an Amazon DynamoDB table, so all microservices share the same baseline configuration. Additionally, the company's finance department mandates that all AWS resources provisioned by the CDK must automatically receive a standard set of cost allocation tags, for example, cost center and environment. Which approach meets these requirements? Options. Option A. Create AWS CloudFormation modules for the architectural patterns. Deploy each microservice using the CDK by referencing the modules. Use the CDK.TagManager construct to append tags to each individual Lambda function and DynamoDB table. Option B. Author custom Level 3, L3, CDK constructs that encapsulate the common infrastructure patterns. Instantiate these constructs within independent CDK stacks for each microservice. Use the CDK tags.of app.add Method at the CDK app level to apply the cost allocation tags globally. Option C. Define the infrastructure using AWS Serverless Application Model, AWS SAM, templates. Import the SAM templates into the CDK app using the CF and include class. Configure resource tagging policies in AWS organizations to enforce the tags. Option D. Author custom level 1, L1, CDK constructs for the baseline configurations. Deploy all microservices in a single monolithic CDK stack. Use an AWS config managed rule to automatically tag resources after deployment. The best choice is option B. Author custom level 3, L3, CDK constructs that encapsulate the common infrastructure patterns. Instantiate these constructs within independent CDK stacks for each microservice. Use the CDK tags.of app.add method at the CDK app level to apply the cost allocation tags globally. Here's why. AWS CDK level 3, L3 constructs, also known as patterns, are designed to encapsulate multiple interacting resources like API Gateway plus Lambda plus DynamoDB into a single, reusable component. This enforces baseline consistency. Applying tags at the CDK app scope using CDK tags.of app.add ensures that all taggable resources generated by the CDK application across all stacks and microservices inherit the cost allocation tags automatically. Using CloudFormation modules inside CDK defeats the purpose of using CDK's native object-oriented constructs. CDK.TagManager is generally for internal CDK usage. Tags.of is the public API for global tagging. C. Combining SAM templates with CDK using CFN include adds unnecessary complexity and does not fulfill the requirement of adopting CDK constructs natively. D. Level 1, L1 constructs are a 1-to-1 mapping to raw CloudFormation resources and do not encapsulate architectural patterns. Deploying all microservices in a single monolithic stack is an anti-pattern. Exam tip. To enforce tags across all resources in an AWS CDK deployment, apply the tags at the app scope using tags.of app.add key value. To build reusable architectural patterns, use level 3, L3 constructs. Next, question number 411. Scenario. A financial services company manages hundreds of AWS accounts using AWS organizations. Security policies dictate that every AWS Lambda function must be attached to an Amazon VPC so that all outbound function traffic routes through corporate firewalls. A DevOps engineer must implement a centralized preventative control that strictly prohibits the creation or modification of any Lambda function if it is not configured with VPC subnets. Which solution will enforce this requirement with the least operational effort? Choices. Option A. Create an AWS config custom rule using an AWS Lambda function to evaluate the configuration of newly created Lambda functions. If the VPC configuration is missing, use AWS Systems Manager automation to immediately delete the function. Option B. Deploy a service control policy, SCP, to the organization root. Configure the SCP to deny the Lambda. Create function and Lambda. Update function configuration actions if the Lambda VPC ID's condition key contains a null condition operator evaluated to true. Option C. Enable AWS CloudTrail organization trails. Stream the data events to Amazon Event Bridge. Create an event bridge rule that detects create function API calls lacking VPC configuration and invokes an AWS Lambda function to revert the creation. Option D. Use AWS IAM Access Analyzer to generate restrictive IAM policies that omit the EC2. Create network interface permission. Attach these policies to all IAM roles assumed by developers in the member accounts. The right response is option B. Deploy a service control policy, SCP, to the organization root. Configure the SCP to deny the Lambda. Create function and Lambda. Update function configuration actions if the Lambda VPC ID's condition key contains a null condition operator evaluated to true. This is the best choice because service control policies, SCPs, are preventative controls that evaluate permissions before an action is executed. By explicitly denying Lambda creation and configuration updates when the Lambda VPC ID's key is absent, null, true, AWS Identity and Access Management blocks the API call entirely. This is the most operationally efficient method because it prevents non-compliant resources from ever being created. The other choices do not work because AWS config rules are detective controls. They evaluate compliance after the resource is created. Deleting resources post-creation can break active deployments and is not a preventative control. C. EventBridge and Lambda represent a reactive, custom-built remediation engine that introduces significant operational overhead compared to a single native SCP. D. Removing EC2. Create network interface stops the function from running in AVPC, but it does not stop developers from creating a Lambda function outside of AVPC. It achieves the exact opposite of the requirement. A helpful shortcut is this. When a requirement calls for centralized, preventative controls across an AWS organization, service control policies, SCPs, are always the most efficient choice compared to reactive custom automation. You have completed set 22 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.